So good afternoon, everybody. It's 3 p.m., so it's time to start our online technology meeting for today. It's the first online technology meeting that we have in 2024. We already have some others online activities in January, but it's the first online technology meeting as itself. And it's a pleasure for me to moderate this meeting on new developments for laser welding. That is a technology with a lot of interesting topics to discuss. That we found a clear motivation last year, and as I will explain later on. And just a few words about EPIC. So this is EPIC, is the European Photonics Industry Consortium. It's an association of more than 800 members, all of them photonic companies or research centers. And our task as EPIC staff is to ensure the sustainability of the photonics business in Europe. So this is a short summary of all the benefits that we offer to our members. We give them access to market reports and also access to new markets to learn what's happening in a new market that they want to address. We help with human resources support, also with financial support in terms of investments, with the technological request in order to find partners and collaborators for all our members, and of course with networking activity like this meeting, where we'll combine the discussion in the technology with the opportunity for all of you to meet different companies interested in the same topic and establish new connections. We will have more EPIC events coming, of course. Regarding the online meetings, we will have several online technology meetings in different topics. So we will cover automotive, lighting, air observation, quantum as well, combining with market reports and other human resources meetings that we will continue doing this year. So combining the technology meetings with marketing, human resources workshops, sustainability meetings as well. So you can check the website for everything related with online meetings. And also regarding physical meetings, we will be at the W3 Fair in Wetzlar, Germany, and OFC. So most of the physical meetings that we will have, or physical events that we will have in the next weeks, are related with these two conferences. And then, of course, we have the annual general meeting in 2024 in the south of France. So all the EPIC members are invited to attend and join this great networking opportunity with C-level attendees from all our members. In April, also, we will talk about agri-foods in Norway. So if you are interested, you can also go to the website, check the agenda, check the topics that we will discuss there, and join if you are interested, of course. And regarding WeLaser, is still in September, but I would like to mention, because most of you are companies that are somehow related with laser processing of materials, we are going to do an in-person event in Vilnius, in Lithuania. It's going to be hosted by our member Light Conversion, and we will discuss about laser micromachining and laser microprocessing. So we are working now in the structure of the agenda. It will be ready in the next weeks. But if you are interested and if you want to join, or if you are interested in also be a speaker, you can just contact me back and we can discuss the possibilities. And just a few words about another topic that EPIC is taking care is participation in DO projects that I will talking with Juan about one of them just before connecting. So we are involved normally in activities of dissemination, communication, awareness for different European Union projects. So this is a summary of most of them we have nowadays. It's not included the last one called Retina, that is also about sensing, multi-sensing developments. But we cover for photonic integrated circuits, freeform optics, medical devices, general optics, the multimodal monitoring solutions, and also laser-based advanced and additive manufacturing. That is the project that is supporting the meeting today. So the idea of this project is to help companies that are interested in or using or exploring the possibilities of laser-based manufacturing in their processes to have the opportunity of testing without big investments. And so you can check the website if you're interested to see which kind of services, consultancy trainings are available at this moment of the project, and apply for one of the bush shares that you can use if you are interested in participating. And as I mentioned, this topic is originated in a meeting that we have last year. So we say thank you to our EPIC member, Presitech, for hosting with Arena 2036, a very interesting meeting in laser applications along battery manufacturing. And in this meeting, we clearly saw that there is a lot of developments related with welding, not only related with the laser itself, but also related with process monitoring, with beam shaping, with well, control of the characteristics of the laser. So there is a lot of things that are now under development, that there are a lot of motivation, for example, in e-mobility to get more efficient solutions and to understand what's happening in the process. So this was the motivation to proceed with the meeting today. And I'm happy to see this supply chain with a lot of registered companies, including several end users and integrators, also equipment manufacturers, laser manufacturers, also cameras and other solutions, consultancy, of course, also investment companies. So it's very good to have this broad spectrum of companies interested in the topic. So thank you to all of them. And you can check this slide later in our website. If you find somebody that you want to be connected with, you can contact us back, and we can do the connection for you. And let's go with the agenda. As I mentioned, we try to cover as much technologies as possible related with laser welding processes. So we have a really great set of presentations from the companies Ophir, Exxon, Presitech, also one slide by new imaging technologies for the photonics, optoprint, Alight, and power photonic. And we, as you can see here, we try to cover all the process monitoring, also the beam shaping, beam management, different technologies that are important for laser welding, and we think that it's interesting to understand what's happening nowadays with them. And yeah, that's all from my side. So I would like to introduce now our first speaker. So it's Nicolas Meunier. He's business and development manager at MKH Instruments in the Ophir brand, and he's going to talk about the high-end laser measurement. So Nicolas, I will stop sharing my screen and the floor is yours.
Hi, Antonio. Hi, everybody. Thank you for the kind introduction. Do you see my screen?
Yeah, everything good.
Yep, perfect. 1 minute. Yes. So hello again, and now we'll see how laser measurement can reduce the price per weld. I want to show you a concrete case study, but before that, I will briefly introduce the company and present the technology and the problematic, and then we can jump to the case study. Hopefully, I'm not going to take more time that planned, but I know I have quite some slides. Yes, so for those of you who do not know MKS is a global provider of process control solution, and it is mainly active in semiconductors, industrial technology, life and science, research and defense. and is best known for its vacuum processing solution. And in 2016, it acquired Newport, bringing to the portfolio laser solutions, motion, photonics, optics solution, and among them, Ophir. Ophir has been a leader in optics and laser beam measurement for more than 40 years now. And Ophir is split in two entities. There is Ophir Optics, which offers laser optics such as mirrors, lenses, and prism, also infrared optics for surveillance and defense. And Ophir Photonics, which is my topic here, which designs and manufactures laser power sensor that measure from picowatt to hundreds of kilowatt, and laser beam profiler that characterize beam of all shape and wavelengths. So the very first question is, why should we measure laser in the first place? Indeed, the quality of laser has become so good these days that one might wonder why it is necessary to control them at all. But they are still made of physical matter. That means that any laser is only as good as its beam delivery system, which means that components wear out and get dirty over time, and as a result, the performance suffers. We have power decreases, focus size will vary, and focus position will change. So in the end, time is wasted, scrap is produced, and money is lost. And we can see here that there is a direct link between the quality of the laser and the cost of the produced part. So this is linking it to the title of the presentation, or to reduce the price per weld. And first of all, a good laser will increase the quality with lower risk of reject, a higher reproducibility, greater traceability, and better documentation. But the efficiency will also increase. The breakdowns are avoided, or you can predict your maintenance and reduce the maintenance time. You can produce more in less time. You will consume less energy, less gas, material, and finally, less. You will do less time. You will do less testing, which is also a time-consuming part of the process. So if you know that your process is right from the laser point of view, you can review the testing. So there are a whole variety of laser parameters that can be controlled, but it's primarily about the process. Which process parameter is the most important? The power density at the workpiece, but it's the power per area. And these are the two main components, the power and the beam area, that we address with the measurement technology. The power density can be affected by the degradation of laser components on the one hand, and if the power degrades over time, the power per area, the power density also automatically decreases. So let's see different power measurement solutions that we have to check the power. There are many types of power sensor. The first one, they do not require any active cooling. They are passively cooled. They can come in different shape and size depending on the power to be measured and the interface to be used. Then there are the air or water-cooled ones. They allow you to measure more power or to measure for longer duration. Among these two families, there are portable and standalone solution that you can operate it with battery. They don't need any separate device to do the measurement, or solution designed to be integrated on production lines to run 24/7 on a real industrial production line, communicating with Profinet or whatever. The power variation was the easy part, so to say. Now let's move on the second important parameter, influencing the power density, which is the beam area on the workpiece. Here it gets complex. The variation can be very dynamic over time. For example, the heating of the focal optics can cause thermal lensing. This is quite common. If the focal position moves in the Z direction, the changing diameter will have a drastic effect on the area. And when the diameter is increasing by a factor of 2, the power density is automatically reduced by a factor of 4 because of the square in the formula. So to measure this parameter, we use what is called beam diagnostic or beam profiling. There are two approaches to beam diagnostic. The first option, as you see here, is a beam splitter and a camera system, or a slit-based or a pinhole system. And this system, they capture individual cross-section of the beam. Since the laser must be in contact with the instrument, the laser power is limited. Otherwise, you will damage the measurement instrument. So it provides a detailed profile of the power distribution in the beam. And to measure the entire beam caustic, the measurement system must be moved along the z-axis and multiple cross-sections of the beam must be measured. This takes time, so dynamic effects such as the focus shift are not detectable. The second option is a camera that captures the relay scattering of the laser beam from the side. So in this case, we're not shooting with the laser on the detector. The detector is looking at the laser from the side, and we call it beam watch. It is a non-contact measurement, so therefore there is no upper power limit. You cannot damage anything. And the whole beam caustic is captured at once and can be followed live. So all parameters can be measured immediately in real time. And you can, in this case, see and track the focus shift. So now let's see the different tools available for each technology. The simpler versions measure only the beam profile. And if they die, they can be combined with some of the power meters we have seen before. Other integrates directly the power measurement in an all-in-one solution. That means these two boxes here, beam peak, beam watch AM, they are doing the beam profiling and the power measurement at the same times. And finally, among those, there are industrial version of beam watch for 24/7 measurements on the production lines, like the one you see on the bottom right, beam watch integrated. So now let's jump to the interesting use case or case study here. In that case, we're speaking of battery welding, more specifically bus bar welding, aluminum, using a 2 kilowatt single mode lather. And here you see a beam watch integrated measurement of a system with a relatively clean protective window on the optic. And this is a 7-second measurement at 2 kilowatt. So on the background, what you can see is a beam profile seen from two axes, X on the left and Y on the right. And the blue arrow, two blue arrows indicate the focus at the start, usually at the workpiece, and the green arrows are the live focus position, so in real time. So you will see that in this case, after 7 seconds, we have a focus shift of just under 3 millimeters. At the focus, where the cursor here, that is the dashed lane, you have a focus diameter of 95 micrometer, which is the expected value, and a power density of 27 megawatt per square centimeter. But at the workpiece, 3 millimeter deeper, we are out of focus. And in this case, we have a bigger beam, diameter of 112 micrometer, and a lower power density of 20 megawatt per square centimeter. So in this specific case, the effect still had an acceptable impact on the quality. That means the connectivity is still okay. But here we are speaking of a machine with a relatively clean protective window on the optic, not a brand new, but not all. So that means that from the start, the system has a focus shift. This is something to know and to take into account that you can compensate when you know it. Now, again, measurement at 2 kilowatt, again for 7 seconds, but in this case with a dirty protective window on the optic. And here you can see that we have a focus shift of 7 millimeter, as well as significant astigmatism. You can see on the orange and blue beam profile that the focus are not at the same position for X and Y. At the focus, the green arrow, where the dashed line is, we have now a focus diameter of 220 micrometer and a power density of 5 megawatt per square centimeter. And at the workpiece, the blue arrow, where the dashed line is, you now have a diameter of 254 micrometer and a power density of 4 megawatt per square centimeter. Compared to the expected 95 micrometer and 27 megawatt per square centimeter, now the diameter is 2.7 times larger and the power density is 7 times lower. So no, with that massive impact on the quality, this has a massive impact on the quality. So there is high porosity. There could be some porosity, some bubbles, but the worst is that in this case, there is no more connectivity. The weld still looks okay, but there is no more electric connectivity. So this example shows how predictively monitoring the focus shift allows to detect the default before they are appearing. So more in the results. So we have seen that a dirty protective window increased the focus shift. This is a blue curve here, which automatically increased the focus diameter, the red curve here. And even if the weld is usually okay, as I told you, the weld depth is insufficient and we have a bad electrical connection. So that means the whole module has to be reworked, which is often not possible. So it has to be scrapped, which is quite expensive. BMWatch integrated measures the laser after each produced part. So the measurement takes only a few seconds and is performed during loading and unloading of the part, so it is stacked neutral. It's not taking production time. Each time a pass-fail output is generated, so you can define the parameters for the pass-fail, and then you have an okay, not okay, and a detailed report is archived. So, and finally, the ability to recognize a trend is used for predictive maintenance, and the protective window is cleaned or replaced before producing bad parts. What you see here is like a chainsaw or like a saw, the blade of a saw, these green dots. Every time the protective glass was replaced, you can see that the focus shift is going back up. When it's going up, that means it's close to, is smaller. And then with time, it's growing, with the protective glass getting dirty, and then every time it's changed. So the limit here was fixed to 3 millimeters as an acceptable value, and every time it was approaching 3 millimeters, it was changed. So as a conclusion, so we have seen that it is very important to know and maintain the laser parameters. We have also seen that there are specialized measurement solutions that can be used to quickly measure the most critical parameters, and especially dynamic parameters such as the focus shift. And finally, we thought that the more regularly the machines are checked, the higher the quality and the productivity, which will help you reduce the price per weld. And I'd like to finish my presentation with the quotation of these two wise men. And thank you very much for your attention.
Thank you
If you have
very
any
much.
question.
Yeah, thank you very much, Nicolas. As Nicolas mentioned, we have time for questions now. So I encourage you to switch on your camera and raise your hand so you can make your question directly to Nicolas. We can start with one question that is typed in the Q&A chat. So Najah George from Photon Automation is asking, how do you measure focus shift in X or Y direction?
We look at the laser. Let's say we have the laser beam vertical. Oh, you don't see it like that. And the camera is here. So we see the whole caustic here. And we have just one camera, but we are able to optically split out of the camera on the X-axis and out of the camera on the Y-axis. So we see both X and Y-axis at the same time. And then we can see how the focus is moving along the Z-axis.
Mm-hmm.
I don't know if that was clear.
Well, Najah, you can type again if you need any other clarification.
But this is quite important to see astigmatism as example.
So yeah, he raised the question. I think you can.
Yeah,
talk.
This technology also for printing, additive manufacturing. I'm just seeing the question being asked. Yes, of course, we've got a compact system, which is what I call an all-in-one system. Beam profiling, power sensor. It is working up to 1 kilowatt without cooling, 1 kilowatt for 2 minutes. But generally, the measurements are much shorter, so you can take a lot of measurement in a row. And yeah, you can install the device. It's a square box, compact square box in the chamber, and do the measurements. Yeah.
Okay, good. I have another question, because when you evaluate the welding to understand what's happening, is something that you do with destructive methods. So you check the beam and then you analyze what happened with the welding. Did you explore the possibility of combining with other process monitoring to understand what's happening in real time, or is it something that perhaps for the future?
I know that some customers have done that. I don't have the results myself. But you're right, this is something we want to spend more time on in the future, yeah.
Okay, good. And we can finish with a typical EPIC question, because you know that we normally ask our members to say what can they do for the others, but it's also good to know what can the others do for you. So perhaps you can tell a few words about what can other members do for MKS and Ophir in this case.
We are always looking for cooperation. We have all this technology available, and the more experience we accumulate, so we would be very happy to come and see you and do some test measurement on some specific applications, so we can fine tune the process and the tools. These tools are now running on many production lines in the automotive industry, but also in the additive manufacturing. So they are quite mature now, but we are constantly making the technology evolve. So if you're interested in partnering or even working with us, we are more than happy.
Okay, very good. So
Thank
I
you very
don't
much.
see any further questions. So thank you very much for the nice presentation, Nicolas.
Thank you, Antonio. Thank you, everybody.
And we can go to our next speaker. So we have Juan Izaza, he's Business Development Manager at Exxon Engineering, and he's going to present the working monitoring approaches for the global laser welding. So Juan, the floor is yours.
Thank you very much, Antonio. Good afternoon to everybody. Hope you can see my screen right now. So I would just like to share some words about our daily business, what we do at Exxon Engineering. Before doing so, I would like to introduce really shortly Exxon Engineering. So for the presentation of today, I would like to explain for those of you that are not really familiar with global laser welding, what we do and how we do this. Then one application, one example, T-joint welding with filler wire, which is just like a kind of motivation why just looking at the wobble and how the wobble is moving and how the energy is divided on the surface of the material. It is important to keep the quality of the joint. And then two approaches, one using a camera and the other one using an infrared camera. So both using cameras, but one is a visual camera and the other one is an infrared camera. And then after that, the conclusions. So as I said before, we found that Exxon Engineering already since 5 years. It was an interesting approach for us because we were dealing before in other companies with integrating sensors and having always some kind of issues and challenges integrating high-speed sensors with the laser, with the machine. And we said we would like to make it a little bit different. We would like to have a solution so that we are dealing with these three worlds together. So electronics, we develop our own electronics at Exxon Engineering. We develop the embedded software that is running on these electronics, and we apply this mainly to laser applications, not only, but basically this is our bigger application scenario. So Senso, right now we've been developing, or we came from this initial status developing control electronics to optics, and right now we're going into a more bigger application area where we are offering completely solutions for laser welding. So for those of you that are not really familiar with wobble laser welding, how do this work? Basically, we just move the beam on the surface using mirrors. In many of the cases, we use 2 mirrors, but it's also one case where we use 1 mirror to move it in both directions. So we are somehow wobbling. The word itself is like going from one side to the other side, making different geometries. These geometries are usual, they are described as a circle. Circles are the most used wobble technology or most wobble strategy. But we can also do, of course, ellipses and lemniscate and basically infinite geometries. Basically, we define using lines, using splines, how the laser is going to move. And at the end, we have a wobble strategy. How do this look like on the surface? This is an example of a conduction welding application using aluminum. Basically, what we do here is an ellipse. The frequency is higher than 200 hertz. And what we try to do is to move really fast so that we are reducing the dynamic at the same point. So we're just moving and moving and moving around this area so that at the end for us it's important to define the wobble type, what we're going to use, for the technology, for the application, but not only the wobble type, it is also important to keep an eye on the frequency, how fast we are repeating this movement on the surface. And of course, also one interesting approach that we're following, the energy, which is at the end, the power over the time that we stay at the same point. So it is not only possible to change the figure, how we are wobbling, but we can change as well the different speeds and powers at different segments over this this figure. So as I said before, I brought today just an application case, just as a motivation. Basically, if you're familiar with laser welding or with welding T-joints, you have a really good definition of the deep penetration throat, how deep you need to go into the material, but also the nominal throat thickness. This is just an example. I just put some numbers on the picture so that we have an example of how we define or how our customers are defining this. This is a work that we've been doing with the company Alpha Laser together. And basically, if we go to an application where we don't use a wobble, let's say, yeah, we're going to try to weld this application, to weld these two metal sheets. This is an inox material. Then, of course, if we have the right amount of energy, we have the right amount of laser power, if we have exactly the diameter, the focal length, and so on, we're going to go deep enough, but we're not going to have exactly this throat geometry that our customers are asking about. So this is just an example how, let's say, wobbling could be an enabler also for future applications in structural welding. Before we start doing this, we of course analyze using cameras. This is just a video of how we using a wobble strategy. This is a lemniscate, the most typical strategy in those cases. We just wobble, and once we wobble, we go further steps and we analyze how deep, which kind of laser power do we need, the width, and so on, and how we cannot affect the surrounding areas of the T-joint, so that at the end we're able to have, let's say, an acceptable deep penetration, an acceptable throat geometry, and also an acceptable distance over the surface. So let's think about, of course, this is going to vary depending on which angle are we welding. This is a welding strategy done with a robotic arm. So it is also important to have access. But basically what we see here is a well-defined laser weld joint, so that we can say, okay, this is working well. But it is important to understand that the stability of this result is depending, as I said before, not only in the frequency, but also that we keep this wobble strategy along the path, and that we keep also the position related to the filler wire at the exactly position that we had at the beginning. So also related to the presentation before, this position, how deep and the effective focal length is here. Let's say if we extrapolate to the X and Y position of the laser beam, it is important as well to keep this position. So in our laboratory setup, we have integrated two cameras. As I said before, basically we use in this setup two mirrors. So we use a galvo scanning mirror, or two galvo scanning mirrors, so that we are using, we're integrating a thermal camera in the upper part. So when we have the reflection of the energy, let's say the thermal image is going back to the camera. So we are seeing on axis, we share the same path of the laser beam and of the thermal camera, and we do it as well for the visual camera. So we can see every time and all the time how the beam is affecting how the weld is working and how we are melting the surface. One of the challenges that we have had before during this integration, of course, is how the cameras are centered, how the different wavelengths, how the different lens and so on are giving us an image that is really okay for doing this analysis. So basically, it's not only important to have a possibility to process all this information, but the optical setup is really important and is a decisive for having a good monitoring solution. So this is another work. We did it also in a project together with the Research Institute LoRTech, in which we said we would like to be able to identify 5 kind of wobbles using convolutional neural networks. So using deep learning technologies, which let's say are state of the art right now. And because we're able to integrate cameras, we would like just to identify how these different wobbles are performing on the surface. So we define 5 of them: a small circle with a diameter of 0.5 millimeter, a bigger circle with a diameter of 1 millimeter, an ellipse in one direction, and the same, but just 90 degrees to the direction of the machine speed. And then, of course, the well-known lemniscate or infinite strategy. So in this case, it is important also to understand that we're not using exactly the same amount of power for all of them, but we are using exactly the same fit rate, and we're trying to keep as well the frequency for all of them. So I would like to share some of the results. So the monitoring approach in this case was done using YOLO UV8. So we took the images, we identified the images, we labeled the images. At the end were more than 1,000 images, and then we just tried to understand if the system is going to be able to identify, of course, with the right amount, with the right optical setup, because we need to have an external illumination and filtering. And in this case, I would like just to share two of the cases of aluminum welding with this setup. So on the right side, you see the lemniscate, and basically the system is performing well, even if you see at the beginning that the geometry of the lemniscate is not exactly the same as at the end. But on the right side, you see that those are some errors that we can find on the edge of the aluminum sheets. I hope you can see it here. At some point, there was just a small amount of extra material. And it is really important to be able to count and to be able to identify these deviations, because this deviation at the moment that we are welding could represent a less welded or a not welded or not a deep penetration that we were trying to reach before. So this is an approach how we are being able, using cameras, using visual cameras, using filtering, and using external illumination to identify and to count how the welding and how the wobble is performing at every moment. In this case, we're using shielding gas argon. So what you see here is basically the tube, which is just putting really in the front of the weld, the argon shielding gas. So if we go to the approach of using infrared cameras, which is a little bit different, I would say it is a little bit more difficult to understand for the user, because we don't have a big spatial resolution. We have a big temporal resolution, but basically we have a 128 by 128 pixel system, which is able to measure at 4,000 frames per second. From that point, we need to define a region of interest, because we are not processing all the information. And in this application, what we did is we just used 25 by 25 pixel. And what you see here is the sequence of what the camera is seeing exactly at every 1 divided by 4,000 second of the image. So, of course, if you see every image, the information of every image is just the beam moving around on the surface, and this is not enough information for us. So if we put a several amount of images, depending on the frequency, how fast we're wobbling, in this case, I think it was 13 images, you can probably identify, making a stack of images, that this could be something similar to a small circle. If I compare it to a bigger circle, probably if you're really good, you will say, yes, probably this is a circle. But let's say for an user, for a person, it's not really user to identify if this geometry is well or is good or not. If I compare it with an ellipse, it's going to be the same situation. So making a stack from different images, it's quite complicated. More or less, it is possible to identify that there is something similar, but this is just only because we know what the geometry was before, but not really because we are able to identify it just from the image. So for this, we just try to use 3 ways of using deep neural networks. In this case, I just present the comparison of 3 results. Basically, in these 3 approaches, we use a convolutional 2D into the neural network. And the idea here is that we tested with 40 images, and the actual wobble pattern is just you see in this confusion matrix is on the left side, and the predicted wobble pattern is just on the lower side. So if you take into account that we are just making a stack of images, so similar that how humans are understanding how to analyze this, we are not that wrong. Yes, there are some situations where it could be better, but let's say it's performing more or less well. But we said no, we would like to go even to a better result, and in this case we went to the second approach and to the third approach. In this case, we're using convolutional long short-term memories in 2D. So basically, we're introducing in both of them not only the spatial resolution but also the temporal resolution, so that the system is just taking into account the image before. So more or less similar to this approach, but in this case, we're making an image from the stack of images. And in this case, we're taking every picture or every frame as it is coming from the camera. And what you see here, comparing both of them, is that we are performing quite well. This is something that is possible to do it online. So we are getting the images online from the camera, and we are able to identify if the pattern that it should be doing is right or not. Of course, we're going one step forward, and we're identifying what happens if we are not identifying the shape that we would like to or that we have in the list, because at this moment we are, let's say, out of the stable process. So this was my presentation, what I wanted to share with you. So I just wanted to present that wobble laser welding serves as an enabler for various applications using filler material, and also, of course, without using filler material. For us, it's really important to keep the constancy of the wobble beam. So not only thinking about how powerful is the laser and if we are or not in the focal point, but as well, are we doing exactly the strategy that we defined? And as I said before, using cameras, visual cameras, requires a little bit more of extra setup, illuminations, and filtering. But in our eyes, it really represents a solution compared to more complex sensor integrations. Of course, if we can use both of them, we're seeing in different wavelengths, which is really positive. And for us, the most robust application is using infrared cameras, because we have a higher dynamic range and we have a high-speed solution up to 4,000 frames per second, which is really positive in our eyes. So with that, thank you very much for your interest and the possibility to present our activities on this area. And yes, if you have any questions, please feel free.
Thank you very much, Juan. So we have time for questions. I can start with a question about the power you use in the different shapes of the wobble, because at the end one circle is small, the other is slightly bigger. In the infinite, you pass a couple of times for the same area, and I see that the powers are more or less the same. It's slightly different. Will it make sense also to evaluate different powers, or this is the powers that you choose are optimized for these shapes?
Exactly. So the power that we use are for welding results that should be working well. So we just did the preliminary identification of the parameters, and we just came to the conclusion that this power are exactly the necessary power for welding both sheets. In the case of the aluminum sheet, exactly. Exactly.
Okay, good. Any other question? If not, thank you again for the nice presentation, Juan.
Thank you very much for the interest.
And we can move to our next speaker. So I would like to introduce you, Marcus Kogel-Holaker. He's head of department R&D projects at Precitech. And yeah, you are faster than me, so you already share the screen, Marcus. So the floor is yours.
Yes, I hope everybody understands me. Good afternoon. Thank you, EPIC, for the invitation. Thank you all for joining this wonderful format of online meetings. I quite remember very well the pandemic times when all that started, and EPIC was the one who keeps us all together with weekly meetings on all possible technology areas. Yes, today we talk about welding, still a very interesting topic, because welding is always, let's say, project related. So you have to always discuss with the end user, with the customer, on how to really be able to solve his problem and to match his needs. So for those who don't know Precitech, maybe there are some in the audience. We are a company which is not an SME anymore. We slightly grew over the years. I'm with Precitech since 28 years right now. So we are about 750, a little bit more, all over the world. You see that we are widespread, and we are active in those areas of the globe, which we see is important, and where the photonics industry can play a major role, which is the US, which is Europe, and which is definitely China. So we have just released Precitech India, which maybe is also of interest for some of you. India may catch up in the near future and will play a much more important role than it was in the past. And so we are quite happy to now have founded Precitech India. So as I said, we are small and medium enterprise. We are family owned, and we reinvest a lot of money into R&D. We are quite happy to have a lot of patents, which is protecting our work, hopefully. And this work is in the key areas of laser technology and 3D metrology and sensors. This is what will be the content, more or less, of my presentation. You see some numbers here in the upper left, lower left. They always change, but luckily they change in the positive region. So we are growing, and our revenue is also growing. So I will talk about ScanMaster today. Why I talk about ScanMaster? This is the solution which we provide these days for most of the e-mobility applications. And this is also one of the systems which was more or less born during the pandemic. And as you already see on that picture here, it comprises more or less all of the technologies which is Precitech is famous for. It's components for cutting, components from the sensor part, which is Precitech Optronic. We have the famous laser welding monitor, LWM, here inside. And we also have camera technology. Precitech has also a subsidiary in Switzerland. For those who have the globe still in mind, there is a quite important part of Precitech R&D happening in Switzerland. This is called Precitech Vision, and all the camera activities of Precitech are going on there. So this, what we call one-stop solution, is an all-in-one 2.5D scanner. You will see later on why it's called 2.5D. And it comprises all Precitech sensor technology for pre, in, and post-processing. We try to compress all the user interfaces in one graphical surface. And so from that GUI, you can control the camera, you can control the OCT part, you can control the LWM part, and you can also control the post-processing part. So why we call that one-stop solution, or why does it comprise a lot of Precitech knowledge? So we are using an industrial scanner, which is not a Precitech scanner. We are not famous for scanners. That's why we are using one of the most robust scanner technologies on the market. But we are famous for laser cutting. And so one part of the Scan Master is the upper part of the Precitech Pro Cutter, which is the motorized collimator. So this is the 0.5, so the half D, which we can put on top on the 2D scanner. So that's why it's 2.5D. So we are able to move the collimation lens, and that's why we are able to correct the focus spot position in Z. A lot of knowledge of the Weld Master is in the Scan Master, which is mostly also the knowledge on coating. So as you may know, all the sensor technologies need a special window, a spectral window, to perform best. And this is a question of coating, and that's why we also have good contacts to famous coating companies all over Europe, which can supply us the best windows and the best beam splitters in order to have the best performance on all the sensors. This is true for the LWM as well as it's true for the camera part. And so this is what we call Scan Master. So I said already, all important areas in laser welding are covered by the Scan Master, which is the pre-process area, where we do part detection based on vision, based on OCT, when we can correct all important modules in order to, when we switch on the laser, have the best beam material interaction. In the in-process, we have the monitoring part, which is the laser welding monitor, LWM, based on photodiodes, and the laser power monitor, which is what we see the best position where we can at least get specific information on the laser power, which is going through the optics onto the workpiece. And in post-process, for sure, we can do some more monitoring, more measurements on the seam geometry, which is photodiode based, which can be camera based, whatever you see. So this is what are the technical specifications of the Scan Master, and this will be mostly the idea of how the Scan Master will look next year. So it's not only the visible components, it will be much more nicer. But we see that most of the applications will happen in the infrared area. That's why in the first run, we will apply that, or we provide the Scan Master for 1 micrometer lasers up to 8 kilowatts of continuous power. Different focusing, different collimation lens, different theta lenses, whatever will be important for the process. The set stroke here is the one which we can guarantee with the motorized collimator. You see the dimensions and the weights, and for sure there will be applications where these numbers will not fit, and we will have different configurations on a request. But what is of main importance these days is that we are also able to apply beam shaping. And that's why we are partnering with K-Labs. You may have seen that on the Photonics West and on LinkedIn, parallel to Photonics West. So K-Labs is providing with the Canunda high power system a very high quality beam shaping solution, 99% system transmission, because it's based on reflective optics. We benefit on the really less focus shift, on the high quality of the focus of the beam shape. That's why in all the work we have done in the past, in the last 2 years on industrial level, and before that on R&D level in European projects, we have seen that it's a fully industrial solution going up to 16 kilowatts, which is important for us when it comes to extreme high power applications. And one of the best things of that solution is the excellent depth of field, which we haven't seen with other solutions these days. So let's go to one of the applications where we apply the Scan Master, which is a cell contacting application, one of the famous applications in e-mobility. There are some limitations in that process which we have to cover, and we can apply all the sensor parts. So in green, you see the vision, which is the pre-process, which is the camera technology. We can easily find the positions of all the important parts in the contacting application. Based on that information, we can directly set the regions where the weld needs to happen. We can apply the weld. We can measure with the autofocus, with the OCT, the set position, can apply the right focus point, and then perform the weld. So this is all based, an excellent weld based on all the sensor technology, which is important. Just for your information, for example, the vision system to see the positions of all the cover part and the weld part is based on a texture-based analysis. So typically the parts are made of different material, or the material is differently structured, and this is what we see with our camera, and that's why we can very accurately see and distinguish different materials. For sure there are some let's say gray zones. Typically it's not always 100% aligned, the cover part with respect to the in that case cylindrical cell. So if it's completely out of range, we can easily stop the process or do not perform the weld, and just bring that information out to the customer that there is something wrong with the clamping or with the position of the contact, and that can be corrected afterwards. So let's talk about the set position. Even though the Canunda system is providing excellent Z-focus constants over plus or minus 3 millimeters. Sometimes maybe there is still the need to apply the autofocus, and so if you see something like that here with a poor Rayleigh length, for sure in these two situations you will not perform an excellent weld, and that weld will not really match the customer specifications. That's why we do need to do some measurements, and we do need to apply that autofocus. And this is quite easy with the OCT in the Scan Master. You see that, for example, for the mechanical strength and the electrical conductivity, the usable focus range is different than for the weld depth and the intermetallics. So if we combine those two regions, the residual usable focal range is shrinking dramatically. So we only have plus minus 1 millimeter of residual focus length. And this is what you also see here in the cross sections. So if you exceed these limits plus minus 0.3, you see that we directly run out of the limits, and the weld performance is not good. I have to admit these cross sections and these welds haven't been performed already with the Canunda from K-Labs. We will do that, and we will provide a new slide in the near future on that specific applications with the new beam shaping solution. This here is just a video on, I hope that video will start on the typical application which I was talking about. So this is what we do in our lab with just a very, very basic clamping tool. I will turn down the music a little bit. So you see, we actually have worked with beam shaping before with the NFX laser from Enlight, but now we have seen that is with the Canunda, it's definitely a better solution. So you see here in the pre-process, we do the measurement of the positions. Then we apply the welds. We have seen the positions. We have seen the set position. We can correct with the autofocus the set position. We have the process monitoring in process, the LWM, where we do process slide temperature and back reflection and the laser power. And in the post-process, then actually we can see that again. So that was more or less my contribution to the EPIC meeting today. So one additional remark, we also work on AI applications. The time was not enough today to talk about that topic. We are quite strong in AI applications based on the photodiode measurements, and we can now provide information on the mechanical strengths as well as on the conductivity, all based on the photodiode measurements. And this is hopefully what you take home. So we see a high diversity of laser concepts, and we see also a lot of challenges in industry, which makes us being able to provide flexible and application-specific solutions. I just used again that picture, which I have generated in 2016 or 2018, I don't know anymore, where I also said was of the opinion that application-specific intensity distribution is crucial for processes. And now we are able to provide that in combination with the K-Labs Canunda solution. So we can say the photons, we can tell the photons at what position they have to interact with the material to provide the best quality, to provide the best laser weld in the end. And we also apply fully implemented sensor technology to be able to control the quality and to make the customer aware that if we applies Precitech technology, he will in the end have the best solution. So again, the question afterwards to you and to the audience. So what can we do for you and what can you do for us? And before I thank you for your attention, we are hiring. So if you scan that QR code, you can directly see open job positions at Precitech. And we would highly welcome you for those who are interested to work for us in our team. Thank you very much, and I'm open to questions.
Thank you very much, Marcus. Great presentation. We already have a question from Marel Holding, so perhaps you can do the question directly.
It's in the chat, I guess.
It's in the chat already. Yeah.
Okay. So
there are two questions. So first one is, can you elaborate on the maximum dimensions of the scanner X, Y, Z? That's the first question.
I will put it in the chat. So I will find that. You will get the numbers in the chat. Okay. No problem.
And the second one is a little bit more tricky, perhaps. In case the scanner detects sharp edges, such as scanning or knife edge, does this influence the scan data? So it's still functional when you have this situation.
Yes, it is.
And I also have a question from my side, because I remember that when we were in Stuttgart, there were also some presentations that were talking about combining different wavelengths in one solution to optimize the welding process and so on. You mentioned that this head is basically thinking in the 1 micron laser. Do you have in mind also to explore options in case of the cases that people combine visible with the near infrared wavelengths for certain processes?
I would just say, though, from what I get from the sales department, we concentrate on 1 micron. With the sensor technology, it's different. So our sensors are capable to also work in the visible, for the visible lasers and for the visible laser processes. But the Scan Master, from what I know today, will be in the first hand purely developed for the 1 micrometer lasers and not for the visible lasers like blue or green.
Okay. I don't know if there is any final question for Marcus.
Yes, I have a question. Hi, Marcus. Nice to see you here.
Yeah, nice to see you.
So I heard that you guys are able to integrate K-Labs on a Scan Master. So if I want to change the beam profile or beam shaping with using Scan Labs, like what I need to do, is there's like easy way to replace those beam shaping optics? Because, you know, it's going to be really tricky if I not decide to which type of beam shaping should I purchase.
Okay. So first, we will provide the best beam shape for your solution. Because at that point, when the customer is approaching us, we already have our database and the knowledge on what is the best for that solution. If there is the need to change the beam shape, in the end, it's 2 mirrors which have to be exchanged, which could be done in a flow box on site. That we have to take care of some of the, let's say, crucial things with respect to cleanliness of the beam path. That's why I say it has to be done somewhere in a flow box. But it's not more complicated than changing a fiber in the collimator. So if this is really needed, but what we have seen and what we have gained during the discussions with the customers, they don't want any more degrees of freedom, and that's why being it's good to be flexible on the one hand side, which is important, I think, for laboratories and research in this, institutes. But if we talk about a industrial application, every screw you can turn will be turned and will bring the process out of its desired process window. So that's why we say a fixed intensity distribution is the best solution for the customers, and we will provide the best solution for that application.
Great. So thank you for the answer. And Marcus, you can perhaps check the chat, the first question from Paul, and so you can give the answer.
Yes.
This way. And we were talking about different solutions for monitoring. One, for example, mentioned about the use of infrared cameras. So I would like to introduce our one slide that we have for today from the company New Imaging Technology. So Francois Coursaguet, he wants to join to share with us some information about their shortwave infrared imaging solutions. So Francois, you can share your slide with us. I think you're muted right now.
It should be okay now.
Yeah.
Okay, so do you see my slide correctly?
Yeah, we see the slide.
Okay, so in just in a few words, NIT, we're a small business in the south of Paris. So we design components. So we are not in the application field. So even if you address the welding field, we are not a specialist of the welding field. But we design shortwave infrared sensors and CMOS sensors, also cameras that go along with our sensors. And we address the industry, but also defense security, air and space, and also scientific applications. We are already very present in the welding industry for our CMOS and our black and white and color CMOS sensors. We have our customers that integrate between 300 and 500 cameras per year using our sensors. These sensors have something very specific, is that they have a native HDR logarithmic pixel, which is inside each pixel of our sensors. So we basically are never blind. So here you can see examples of cameras that integrate our sensors and different images where you can really see the beam and see the what you're looking at. So that's the interest of having this very high dynamic range pixel. The focus today is to discuss about how shortwave infrared can also be beneficial for the application. So the benefit of shortwave infrared, it's a wavelength that is between the near infrared and the thermal 3 to 5 or 8 to 12 micron wavelengths. And so what is the interest of having this waveband is that it gives both visible information, reflective information, but also thermal information for any thermal temperature that is above 200 degrees. So what's the interest of having this thermal information is that you can, during the process, you can control the temperature or the homogeneity of your pool. You can also control the temperature decay, which is also a good sign of the quality of the welding. Another feature of interest could also be to be able to control, and we know one of the customers does this, to control from the outside of tubes. If you cannot put cameras inside of small tubes, you can control the thermal aspect of the welding outside of the tube. Now, the second question is why logarithmic? So the HDR logarithmic response interest is that it captures a complete range of temperatures from 200 degrees to 1800 degrees in a single capture. So you no need to adjust the exposure time or whatever. With a single exposure time, you can capture this complete range of temperatures. And so you have a very robust thermal information as well as visible information in the same image. So this gives a very nice features in order to be able to control your quality during the process itself. And so why NIT? Well, first of all, we have this the dedicated logarithmic pixel response, which is a patented response. And we've developed a complete range of ruggedized and cost-efficient shortwave infrared and gas sensors, and also cameras that can also integrate a Belletier, a tech inside, so that you could regulate the temperature, and so we can calibrate your camera and thus have the exact temperatures within your melting pool And so to basically we sell for this market essentially sensors and also cameras for some customers, but we stop at this component level, and it's our system and our customers that integrate all the software and the control software that goes with the cameras. So that's pretty much it. I was told that it was to be a short presentation, so I gave you a short presentation of why SWIR is also, shortwave infrared is also an interesting technology for the welding application. And since we've been on this market for the shortwave infrared, we've been growing very quickly on this market for this technology. So
thank you very much, Francois. Really interesting, and I encourage anybody interested in this technology, please contact Francois and the New Imaging Technology team for more details. And we can go with our next speaker. We'll continue talking about monitoring of laser processes. So it's a pleasure to introduce Søren Hollatz. He's technology manager at 4D Photonics. So Søren, the floor is yours. You can share your screen.
Thank you very much, Antonio. Yes, it's again process monitoring. I hope you can see my slides right now.
Yeah, we can do it.
So yeah, my name
I
is...
mentioned at the beginning that this is a very interesting topic. So this is why we have a lot of partners and a lot of members doing these kind of technologies.
Yes, it's very important, and especially with new products such as electric vehicles, we need a lot of process monitoring. So probably that's one issue. So yeah, my name is Søren Hollatz. I'm working for 4D Photonics. It's a small company located in Germany, with about more than 20 years experience in process monitoring. And last year we have announced our new product. And I will give some short introduction to the sensor system and also some results from hairpin welding. So I'll start with the technology by itself. It's a photodiode-based sensor system. So we have some light emission from our process that is going back to our laser head, going into our coaxially integrated sensor system. And then we can evaluate the signal on reference base. So we are doing some good welds and say, okay, there's one that shows a little different signal, and then we can say it's not okay because something has happened there. So that's basically how process monitoring with photodiodes work. And our main goals are to increase the accuracy during this monitoring process, because the pseudo faults are in both cases very, very painful, and that is our most important goal to increase this accuracy. The second idea, or the second goal, especially for this sensor, is not just to say, okay, this weld was not okay. We would also like to say, why was it not okay? So we would like to classify the fault, to give some ideas for the production line. Oh, my clamping device is not working correctly. We had a gap between our parts, or our optics has some contamination. And for this purpose, we have designed a new sensor system. You can see it in the picture, and let me. We can see here the welding process with the light emission that is going back into our laser head. And then it is reflected into our sensor system. There we have the first sensor, first photodiode for the laser radiation wavelength. In this case, it's about 1 micrometer. We have another photodiode that is detecting the visible light, and also one for the near infrared wavelengths. And the last two channels are additionally split into its spectral components. So we have another array of sensors or photodiodes for the near infrared light, and also one for the visible light. So we have 16 channels each. And with this further data, we are able to have a more accurate monitoring compared to our old product, and to hopefully also to the competitors that usually go with 2 or 3 photodiode sensors. So what's the benefit? I already said we have a lot of channels that we can use for the analysis, but we have also developed this sensor in this way that we are able to use it for a wide range of applications that have some process emission. Because the idea is to have one sensor, one hardware sensor for all applications, and to just do some software adoption due to the process or material or wherever you have. So we have tried a lot of different applications, also starting with welding applications for battery cell welding, hairpin welding, which I will show afterwards some results, also bipolar plates or other welding tasks. But we've also used this sensor for laser powder bed fusion or drilling or structuring or coating processes. And we are right now getting some experiences and trying to get some experiences in all kind of markets that are suitable for our sensor system. So our idea is to classify the faults, and for that I've already shown you that we have a couple of different signals available in our sensor. So what are we going to do with these lot of channels? How we proceed with this one? And therefore, we are going to use a combination of channels. So we have the function in our electronics that we can combine a couple of these channels to create a new channel for the analysis, which is behaving in a special manner for example, for gaps or for spatters or for temperatures. And with this one, we are trying to get some more information, and also for the identification, to get some specific channels for the identification. We are basically getting a lot of data, and then we are correlating it with some scatter bands and say, okay, there's some outlier, and there must something happen during this weld scene. This is of course possible to communicate to the machine, to the logical control, and to say, okay, there was some kind of error. And by having this specific classification of the faults, you're able to also have an adopted maintenance action. So you can say how you proceed with spatters. Maybe you can tolerate them and have just some further check if it's okay, or you can directly send it to scrap when you have a gap between your parts, which will definitely have a huge influence on your quality. So with this, we have a list with a couple of benefits that I probably also told you in the last few minutes. We're trying to reduce the scrap rate, of course. I've talked about the pseudo faults. We're trying to reduce the downtime, of course, because we can faster say what is the root cause of our NOK product. And also we can have a specific maintenance call at the end. So that's it about the basics. Now I would like to talk about some results. In this case, in hairpin welding. So the newest generation of electric engines for electric vehicles are built up using hairpin technology. So instead of winding a wire for the stator, you are stacking these pins, copper pins, into a certain frame, and you welded these frames on one end. So there are a lot of challenges during this welding process. Yeah, we have investigated more or less all of these ones, but I will just give some shorter results and start with a good hairpin welding right now. On the left side, you can see in this picture, it's going to be a video in a few seconds. This is pin 1, and here on top, it's the second pin. So we are looking with a slight angle on it with a high-speed camera. And on the right side, marked with this arrow, we can see our measurement during that time. I have reduced the channels to have a better visibility. And I will just start the video, and we see 3 weld seams, one on the first pin, one on the second, and then a combined welding. So, and we can see we have some smaller characterization during this weld, but in general, it's a pretty calm process in this case. And now I would like to show the, maybe the opposite of this process. When we have some isolation on this pin that has to be removed before the welding, you can see that the signals are escalating completely, and also you can see the process is not stable at all. And this is something you can see pretty easy. But there are also more complex faults or happenings during the welding that are able to be that are visible in our data. To investigate this, we have performed welding experiments with the Fraunhofer ILT. They are using X-ray imaging to have an insight into these hairpins. We see them now, one on the left and one on the right. And we are using this data to train our system to get experiences with hairpin welding and how our signals are reacting. To get at the end, of course, more ideas what happens when we don't have this X-ray imaging, because it's too expensive for production lines. So I'll start the video. We can see again one weld seam on the left, one on the right, and then a combination of them. And on the right, of course, again, our data is moving. So that was pretty fast, but we'll have a closer look right now. So we can see a couple of peaks during this weld seam. That's good for us because it's not really an okay welding. We have a couple of pores at the end, and we can investigate a couple of things during this welding. Let's start with this very high peak at the end. You can see here the keyhole visible due to the X-ray analysis, because the X-ray analysis shows us the border of our melting pool and also of our keyhole. So this is the keyhole during the welding. And if I move some slides forward, we can see it is moving on the other side, but we've lost the depth completely. And this breakdown of our keyhole we can see here with this very high peak. And one slide afterwards, we are getting back this peak, the depth of the keyhole. So these are things we are investigating with this data. We can also see the positioning was not really good on this side, so the keyhole is bended. and we probably didn't hit the hairpin in the middle, but on this side. Another thing we can do with the sensor is that we have a look on the near infrared channels. I have excluded 2 of them right now here that we can see in the graph. And what we can see is that they have a different gradient at the end. And with this gradient, it is possible to give some ideas, information about the temperature, because we can build the gradient of it, the quotient, sorry, and then we have kind of a ratio parameter. And this ratio, when it's increasing or decreasing, it gives us some information about the temperature that is, in this case, rising due to the last step of the welding process. And it is basically possible to get also a real absolute temperature, but in this case, this optical setup is not calibrated, so we just can give some relative ideas that we have an increasing edge here. So this is one example for this combination of channels that we are aiming to. And I have also a slide for what we can do with these data with X-ray imaging. Because, oh, that's the video, sorry. Because what we really like to do is we want to skip this X-ray imaging and just have our data from our sensor and can say on this position and there happen these kind of mistakes. So what we are doing right now is using artificial intelligence, having these 4 different categories of errors. And in this case, we have trained this model with our data and also the X-ray videos. And this slide here is the result when we just have our data using the trained model. The model is giving us the positions on which we have a higher probability of these 4 categories: porosity, bulging, piercing, and splashing. And we can see that it basically fits very good with this rough surface structure of the weld seam. Also here, it's everything is green, and also the weld seam looks pretty good. And then we have a couple of mistakes in the surface, and we can also see that our signals and the trained model is showing these results. So these are the things we are doing right now. So as in summary, you've seen what we can do. We can provide a multispectral process monitoring. We are trying to have one sensor, one hardware sensor, for more or less any application that has some light emission, I would say. And we are trying to use this data for the identification and classification of defects, not just for welding, also for other laser-based processes. So what you can do for us, we are always looking for new applications, because we need to prove it that our sensor is possible to deal with a lot of different processes. So therefore, it's interesting for us to get new data from different processes, different applications. We're always looking for scientific or industrial corporations. It would be also interesting for us to get external data to our system, because the hardware is generally able to include an external data channel that can be matched and synchronized with our data to have some kind of a data fusion. For example, positioning data of scanner systems. And of course, due to the start of our new product. We are still trying to increase our capabilities in production and calibration, and also in optic adjustment. And if there are some experts under the audience, we are open for a discussion. So that's it from my side. Thank you very much. Are there any questions?
Thank you, Soren. So we have time for one question. So Paul.
Yes, thank you for this opportunity, and also thanks for the speaker for this this introduction of the technology. Really interesting. My question relates to measuring the electronics. As we know, the electrons have a tendency to flow into sharp corners. And my question is, if we, by means of multispectral imaging, if it would be possible to measure how fast those electrons flow, or that we have an indication how sharp a corner is, if we can translate that with data.
Well, that's a very difficult question. I have, I don't have a spontaneous answer to this one, but we might have a discussion afterwards.
Yeah. Please do, because you stated something about being able to measure the gaps, and like there are companies who are using laser already for handheld gap guns and so on. So that's not completely new. The problem becomes because of well, I wouldn't say reflection, but measuring with a laser the shape of a sharp edge, that always has been a challenge. Yeah, so this is why I'm asking. So I would like to elaborate with you on that later on. Yeah.
Mm-hmm.
I can put you in contact afterwards, Paul, with Soren, so you can discuss by email more detail, or fix a call to discuss with the expert more in detail.
Please do. Thank you. Yeah.
Thank you. Great.
Thank you. Thank you, Soren, for the great presentation. And we can move to our next speaker. So it's a pleasure to introduce Stefano Sarini. He's application engineer at Optoprint, and he's going to present the benefits of single model lasers in aluminum remote welding.
Good morning, good afternoon, everybody. Can you hear me?
Yeah, we can hear you. We see the screen as well.
Okay, perfect. Thank you very much. Thank you very much for the nice organization of the event. I try to be quite pragmatic and synthetic. So here it is. So let's go through the agenda. First of all, brief company presentation, who we are. And I wanted to highlight immediately what we can do for you and what you can do for us. I mean, it's a wonderful sentence that try to identify and to better explain what we can do. So I want to state this from the beginning and not at the end. In these, we will be focused on examples of what are the potential benefits of high power single mode lasers in aluminum remote welding. Finally, some conclusion. So, first of all, brief company presentation. We prepared a nice video that try to explain who we are and what we do. We started in 1999 as a distribution company. We quickly realized that it was not sufficient providing information related with the specific components, but we quickly understood the importance of having specific related with applications that we are going to analyze. Because of this, the company has decided to invest in strongly technical, where each application has some specific engineers that can be focused on this and provide a specific solution and specific problem. This is an important step. What we are looking at currently is our facility that is taking the name of Optoprint Engineering. Optoprint Engineering is the division of Optoprint that is taking care of specific application of each customers. As the market has stated before, it's important for especially welding trying to have specific need, specific So in our facility, not only for welding, but also casting, machining, casting,
Can you reduce the volume of the video? Because we don't hear you.
every type of system. Given this, the aim is to try to provide the customer the best possible solution. With this object, to compensate, to realize an identification of all the process. Okay. So, given these, what we can do for you, what you can do for us is please describe in detail your manufacturing problem. We are going to analyze it to understand the production environment you are located, and we are going to provide you a possible solution for this problem. How do we work and what we do for you? So we perform, first of all, economic sustainability of the idea. We can build whatever we want. But is it really needed a Ferrari to go to the grocery? This is the main question. So if you want a Ferrari to go to the grocery, please, we are happy to help you, but from time to time it is not possible. So first of all, we try to identify the economic sustainability of the solution provided, and then when this is identified, we switch to a technical feasibility. So we identify and we understand the process, we characterize all the process, we select process parameters, we perform pre-production to validate in a more statistical way, and we have a results approval from the customer. When this is achieved, then we switch to the transfer of know-how and of the solution to the machine builder or to the end customer directly. So given these, when all this phase is done, then we will close the project. So we basically, in the automotive engineering department, we work project-based.
Stefano, we hear you really low. Can you be closer to the mic?
I can try. Can you hear me better now?
Now it's better, yeah.
Okay, sorry,
Thank
guys. So let's go to an example of this type of approach. We were asked, always related to the battery field sector, to maximize the working area of aluminum welding plates. Aluminum welding plates were made of 6000 series aluminum that have difficulties in welding. And in addition to this, because of all the problem and all the possible solution available that were also mentioned before, between wobbling, beam shaping, and so on, we were also asked to identify what is better for this type of application. So what we did, for example, for this type of application was a comparison between wobbling solution and fixed spot with and without beam shaping. We used one of our cell fully dedicated with different type of remote optics to accommodate each specific optics for each specific application. In this case, we are going to use zoom optics that allow us to work with the multiple lasers. In this case, we compared fixed spot solution with a maximum power of 3 kilowatt, and we will understand later on why only 3 kilowatt, amplification factor of 2, and different type of energy distributions. From standard laser, introducing beam shaping. We tested different type of speeds. In a similar fashion, we used always 3 kilowatt lasers, but using wobbling, so using a spot with 150 micron. What we kept constant was the overlapping between subsequent weldings. So from 25%, 50%, and 75%. Using wobbling amplitude and using the using a maximum wobbling frequency of the scanner up to 300 Hz, using the same welding speeds. So if we go directly in this type of approach, we can clearly say that independently from the energy distribution used with fixed spot deposition, in most of the cases we had crack formations. Because of the low power density, in some cases we did not have any welding. Because of the high scanning speed, so we are going extremely fast, we were not able to achieve super high frequency related with the scanner, so we were not able to cover this area, while finally we were able to obtain nice and smooth welding crack-free. So we understand that between these two solutions, for this type of application, we were able to use, it was better to use a wobbling approach. Now, we were talking about single mode lasers, but if you can clearly see, up to now we didn't work with any single mode lasers. So given the identified solutions and given the goal to maximize the working area for laser processes, we worked with this type of configuration, so 50 micron spot, 140 millimeter collimation, and 420 millimeters focus length, obtaining a laser spot of 150 micron. Nevertheless, the request of the customer in this case was, I want to enlarge as much as possible this working area. So squeezing as much as possible the fiber size, so moving to single mode lasers, and now we understand why we decided to work and to limit up to 3 kilowatt, because currently most of the single mode laser with the highest power can achieve up to 3 kilowatt size. We can keep the same collimation length, but we can enlarge the focusing distance up to 1050 millimeters or 1500 millimeters according to the fiber size, achieving the same spot size. In this way, we can clearly maximize the working area, and thus we can avoid to use a robotics arm and so on, and we can work directly with a fixed scanner. Not only this, but in conclusion, related to this application, not only with this is the biggest benefit, but it is remarked, the last sentence of this bullet point, the fact that with this other type of configuration, we can move the relay length from, let's say, 2.6 millimeter to up to 33 millimeters. What does it mean? That first of all, we become much less sensitive to eventual focus shift. Secondly, we can be much less eventually sensitive to focus variation of the working plane, especially if we weld thin aluminum foil. And this is a really huge benefit from a practical point of view, in production point of view. In conclusion, we wanted to give you an example of what we can do and how we structure the design of solution that we can provide to our customer. A standard methodology is always used. So first of all, comprehension of the context where the customer is located, and what are the real needs of the customers. Further than this, we identify the best possible solution. Being quite straightforward to an example case that we presented, but we could have had many more, and this is our daily routine. An identification of stable process parameter for welding of 6000 aluminum series using a near-infrared wobbling strategy was assessed, and benefit of the identified process parameter transfer to single mode laser was assessed as well. My main message to all the people here, that I see also some people from the optics side, is that one of the biggest challenges that we are facing is the fact that the limitation of such a long f-theta, long-range f-theta lenses, and also the limitation of high-power single-mode lasers. We do believe that in the future, in both these sectors, big enhancement will be done and big benefit will be achieved from the manufacturing point of view. Thank you very much.
Thank you, Stefano. Now we have time for one question to Stefano. So I have one that is, could you talk a little bit about the challenges of using a high power laser with a nanometer optical fiber in terms of damaging of the fiber, for example? Do you have any issues focusing all the power in such a small core?
Yes, this is one of the big, let's say, reducing as much as possible the fiber takes some really important challenges. Raman effect, first of all. Secondly, the fact that if you start, it's not mainly related with the fiber itself, but from the divergence of the fiber. The shorter is the power and the smaller is the power density, the fiber, the higher is the power density. So we need longer collimation lenses and so on. And this is one of the most challenging aspects that we can do, that we can face.
Okay, so special optics are needed to really get all the power in the final spot.
Yes.
Okay, thank you very much. So there is no any more question. Juan, yes, please.
Oh, yes, I have a really short question regarding the calculation that you did about this longer working distance. Is this just a theoretical value, or this is really based on a data sheet of a f-theta lens with this long focal distance?
Those are theoretical values. One of the limits that we found is looking for such a long f-theta. We do believe also that one of the other important aspects to be taken into account is the fact that, especially on longer f-theta, if you go on the edge, then you got really aberration, and then you could have some problems. Nevertheless, compensation with z-axis, fast z-axis within the optics would be needed in order to compensate for that.
Thank you. Yes, thank you very much.
Currently, we are working with some f-theta of 1 meters that are giving us really nice results.
Yeah, I was just wondering if for those longer focal distances, also pre-focus beam would be an option. So not using f-theta lenses, but you're really using a third axis because you're going really to a long distance.
Yes, would be an option, absolutely.
Thank you very much.
Thank you, Juan, and thank you, Stefano, for a nice presentation. And we can move to our next speaker. So it's my pleasure to introduce Guido Perrone, co-founder and president at Alight, and he's going to present his solutions for high-power beam management. So Guido, you can share the screen and the floor is yours.
Okay, thank you. Thank you, Antonio. I hope that you can see the screen. Okay, so first of all, thank you for the opportunity to present Alight. So thank you to EPIC for the organization, and thank you all of you for being connected this afternoon. Alight is a small company that has been founded quite recently, so at the end of 2020, but it inherits a pretty relevant experience because it comes after the experience of another company that I have co-founded some years earlier and then sold in 2020. It was OPI Photonics. Moreover, since I'm also a professor at Politecnico di Torino, one of the most prestigious Italian technical university, of course, Alight benefits from strong synergies with my research group at Politecnico. So let's say that Alight is a sort of the industrial arm of the research activities that we are carrying on at Politecnico. Despite being a young, small company, a light is organized into, let's say, teams, or if you want to use high-sounding words, divisions, one working on lasers and the other working on sensing. The one working on lasers will be discussed more in details in the next slides. So let me say just a few words for sensing. The team working on sensing is developing a fiber optic monitoring system. So the entire monitoring system from the sensor itself, typically using fiber break ratings, to the entire interrogation system. But the real keyword that brings together these two teams is the word personalization. We have heard before large companies that are providing off-the-shelf solution, really excellent off-the-shelf solution. In our case, we try to find our niche in customized solutions, so solutions that cannot be found directly on the market for special applications. So, for example, the laser team or laser division is working in providing customized, tailor-made laser sources and bench management devices for processing challenging materials like paper, cardboard, and most important for current application, so-called high reflective materials such as copper, gold, and some kind of polymers. Not only, but also in some direct marking application, like for example in textile, fruits, vegetable. You see in the picture that we wrote apple on an apple. Just this can be of interest, not for welding, but to reduce labels and therefore environmental impact. In practice, what can we do? Well, we can provide customized laser sources. What does it mean? It means, for example, sources emitting in the near infrared with some peculiar feature not easy to find on the market. For example, a customer recently asked us to develop a laser diode emitting at a certain wavelength, and we took commercial diodes. We are not fabricating semiconductors, but working with optics, in particular, introducing the wavelength stabilization either through external discrete components, and we are also now pioneering the stabilization through gratings inscribed directly into the multimode delivery fiber. We managed to obtain the required wavelength. We are developing blue laser system, and we will see why later on blue is interesting, and also sort of other non-conventional wavelength lasers, like for example, recently a customer asked us to develop a 100-watt fiber laser into L band, so above 1600 nanometers. Moreover, we also develop devices to couple, switch, and combine high power beams in the kilowatt range. This, I think, is of interest for welding application, because as we know, in welding application, maybe often we have to change the beam, the diameter of beam delivery fiber, so the process fiber, and this can be done by switching between different kind of fibers. Or on the other hand, we could be interested into combining different beams to scale the power or to introduce specific features. We heard before about the possibility of using single mode lasers, and we heard that single mode lasers are limited to certain power, which of course is true. A possible thing to explore could be to combine single mode lasers at slightly different wavelength in a spectral, so in a spectral division multiplexing to scale the power. And we had the opportunity to work with the development of custom devices so far up to 20 kilowatts, but we think that there is still space to increase the performance. But this afternoon, I would like to spend a little more time to present you possible outcomes of 2 European projects in which we are involved that can affect also the welding application, despite these projects are not directly focusing on welding applications. The first project, is an experiment within the Pulsate European project that Antonio mentioned at the beginning. In this experiment, the goal is to develop a compact multi-material additive manufacturing machine, a small one, specific design for artisans' workshop. And being a multi-material means that the machine, with very little change in the configuration, should be able to process different kind of materials, going from high-tech polymers, like, for example, PEK, or highly reflective materials, like, for example, gold, if the artisanal workshop is a jewelry, say. So this means that the machine must be equipped either with a near-infrared source, or if you want to process an highly reflective material with a visible source, like, for example, green, or even better, blue. The role of a light is, in this case, in this project, is to both develop the source and to develop the processing head. And we will see in the next slides how these results can be adapted also for more specific welding applications. The other project in which we are involved is called WISE. It's a project that just started recently, and the goal of this project is to develop an all-in-one machine that integrates up to 5 laser processes for the direct fabrication of macro-scale products. And integrating 5 laser processes means that we have, using a single machine, that we have to combine possibly 5 types of lasers together. So we have to combine lasers having different wavelengths. And again, we go to the idea of combining lasers emitting in the infrared and lasers emitting in the visible, again, green, blue. But also lasers operating at different operating regimes. So, for example, in CW for additive manufacturing or for welding, and pulsed for polishing the surface, for smoothing, or for subtracting. So this means that this project requires the development of specific optics, specific what we can call hybrid combiners, to combine all these kind of lasers together. And Elite roles is in the developing the optical chain, so the entire optical setup from the source to the workpiece. Now, this workshop is dealing with welding application. So how can we use the expertise that we have gained and that we are gaining in working on special projects for welding? Well, in my opinion, the first thing could be into developing hybrid, visible, near-infrared processing heads. This is because, as you can see from the graph that we have here, it's pretty famous in these days, because everybody now is talking about the processing of highly reflective materials, copper, which is critical for the electrical transition, gold, etc. And as you all know, these materials are not processed very well with near-infrared fiber lasers, so laser emitting at around 10 something nanometers. So, for example, 1050, 1070 nanometers. And even worse, even worse, not only those materials absorb, poorly absorb at those wavelengths. But even worse, for example, copper, you probably know that changes is absorption depending on the temperature. So when you start the welding process, the absorption is very low. So you increase the power in order to start the melding. Then suddenly the absorption increases, and this produces vaporization and sputters, and in the end, a poor quality of the welding, or in general of the process. A solution can be to switch to wavelengths that are more absorbed, like, for example, in the visible, as you can see from the plot, green or blue. Even better blue than green. However, we have some challenges. Well, infrared and visible light, they are very far apart wavelength, and this poses important challenges to the development of optics, not that much from the point of view of the coating, which can be in any case overcome this limitation, but rather in the performance. If you think of an f-theta lens, for example, that has to produce the same performance in the visible and in the green, if you want to combine these two wavelengths. So another critical thing, if you want to combine the benefit of near infrared and blue laser light, is that they typically have very different beam quality. In particular, the light coming from the near infrared fiber laser, as we heard also from the previous speaker, can be single mode or near single mode, so the M square can be very small. On the other end, especially if you are thinking of blue laser, they come from diodes and with a very poor quality. So the challenge is, how can you deal with these two things together? And to solve this challenge, we have developed a new type of processing head that has a patent pending solution implemented to deal with beams having very different quality. And we are currently testing this solution in a new type of a hybrid process, in which we can combine the benefit of blue and the infrared. So blue can be, for example, used to increase the temperature, and then you continue the process with the higher quality near infrared. At the moment, the solution is pretty bulky, so it's not as elegant as the picture you see on the upper right part of the slide, but we are working toward that. Another outcome that we expect from our experience that can be used for welding is a derivation of the approach that I was mentioning before for the WISE project, in which we have to combine several types of lasers. So the idea is, for example, that we have to combine together a visible or near infrared, or both of them, using the previously mentioned approach, CW beam, in the order of hundreds of watts if you are thinking of blue, and probably kilowatts if you are thinking of the infrared, together with a pulsed laser. Pulsed laser that can be in the order of nano to picosecond usually, or at least the kind of application we were targeting was in this range. At the moment, we have developed a prototype of a combiner that can take as an input a fiber with a standard QBH connector coming from the CW laser, while the pulsed laser is delivered in free space. But in the future, we plan to have an all-fiber solution that could be, for example, using hollow core fibers to better deliver the pulsed laser. Of course, an all-fiber solution could be more compact and therefore reduce also the weight of the processing head and improve, therefore, the mechanical performance of the system. And this could be, for example, of interest if one wants to combine welding process with maybe some polishing processes that require pulsed lasers. The question that usually Antonio asks is what can we do for the others and what the others can do for us is easy to answer. Well, we are a small company, so any help in testing the proposed solution, any cooperation in proposing new technologies, new technological challenges is welcome. And what can we do for the others is to let our expertise in beam shaping and combining to put at the disposal of the others our expertise. So in particular, if you have a non-standard problem for which you need a specific kind of personalization, so you don't find off-the-shelf solution. And this is everything I wanted to say today. So I thank you again for your patience in listening. And if you have any question, I'm happy to answer.
Thank you very much, Guido. So we have time for questions. I have one question regarding this visible and near-infrared processing head. Well, I don't know in your case, but sometimes the blue-green lasers can have some issues with the shape of the beam compared with the near-infrared that is quite mature technology. In this combined head, do you think that special optics are needed to not have or to reduce the influence of the beam quality of one laser compared with the other?
Yes, this is definitely true what you are saying. Of course, the different quality of the two beams is a problem. But if you think of an application in which you want to combine the two beams, so sorry, we have to distinguish between a case in which you're saying, I want to use let's say the same architecture with different wavelengths, but not together. So we can try to optimize the general architecture, and then we just change a length or two depending on the wavelength you want to use. Another thing is if you want to use both wavelengths together, because in your process, for example, like in processing copper, I'm not a processing guy, but as far as I heard, in processing copper, it may be interesting to have blue for preheating and then finishing the process with the infrared. In that case, typically the constraint on the quality of the blue is important, but not so critical because you accept a larger spot of the blue because it just has to preheat and not doing the fine features. But it's true that in general, the difference, the largely different characteristic between the two beams play a major role. And this is also why we developed this let's say, new solution, this patent pending solution, for which we try moving by some lenses to compensate for the different quality and therefore shift the complexity from an optics that maybe does not exist, that can do everything at two such different wavelengths, into a slight complication in the mechanics, but still doable.
Okay, yeah, thank you. Thank you. It's interesting that you are thinking also in this kind of combination of optics.
Thank you.
So, yeah, we have another question from Naya.
Yeah, thank you for a nice presentation. Now, when you have one single compact welding head to combine two wavelengths, now your focus position is going to be different, like between the two wavelengths. So how are you going to solve that problem?
Exactly. As I was saying, we have to add some movement in the lenses, so we can compensate for that. The two beams share part of the optical path, but not all of it. I cannot go into the detail because of the patent, but we are pretty convinced that we found an acceptable solution for having a good compromise. Of course, you never have the optimal situation, but you can obtain a good compromise.
Okay, so thank you again, Guido, for the nice presentation. And let's
Thank
go
you.
with the last speaker today. Sorry that we are quite late in the schedule, but I want to introduce you. Alex Griffiths is lead engineer at Power Photonics, and we are going to talk again about beam shaping. That is another very interesting topic in laser welding.
Yeah, thank you for the introduction. Can you all hear me and see my slides?
Yeah.
Good. Yeah, so I'm a lead engineer in product development at Power Photonics. We are an optics manufacturing company. That's one of our specializations is in beam shaping for high power applications. So what I'm presenting today is some work that we've done in collaboration with WMG at the University of Warwick to demonstrate some of our new beam shapers and the advantages they may bring for enhancements in laser welding and the quality of laser welding. So we manufacture optics and fused silica. We have a laser-based direct write manufacturing process that lets us make fully freeform optics. Well, the two key advantages of our manufacturing is, well, the freeform nature. That means we have no symmetry restrictions. We're not limited to rotational symmetry or mirror symmetry at all. And the laser-based machining process means we retain the high LIDT properties of bulk fused silica. So these two strengths play nicely into laser welding, which is why we've been working with WMG to see how we can apply these in a way to solve a particular problem. The problem that we've addressed in this work is the welding of aluminium 6082. As has been mentioned, the welding of some of these aluminium alloys is difficult. The current techniques use filler wire, so you're adding extra material into the process. It's quite complicated, it can be quite wasteful. And 6082 is quite sensitive to cracking along the line that you're welding. So in this work, we're aiming to add some benefit through beam shaping to get a laser weld only process with no filler wire, and show some improvement into the issues around cracking. I've got the details of the optical system and the welding setup in this slide, but I won't go through these line by line. I just want to highlight in particular that the optical setup was quite a straightforward modification. In the laser head, there's a protective window between the fiber source and the collimating lens. What we've done is taken the dimensions of that protective window and machined our optic into the same size substrate. So installing this is a straightforward case of taking the protective window out, replacing it with the beam shaper. There's no need to change anything in the full optical train. There's no large components to add in, no complicated systems to put in place. It's a straightforward swap of a plate that is replaceable. So there's two different beam shapes that we're looking at here in this work. The first of them is based on our light tunnel generator optic. So we've seen already, it's quite widely known that the welding can be improved with a core and ring setup of your intensity profile, where you have the central core doing the weld and this ring of intensity that applies some heating around to the surrounding area. What we have with the light tunnel generator is we can generate a light tunnel where this ring profile propagates through focus. So we've made a modified version of that where we allow the unshaped beam to propagate through, and then there's the light tunnel around it. So you get this core and ring geometry of your shape, of your spot shape, but it also propagates like that for quite a significant distance. So the depth of focus is improved. We've gone for a 50-50 ratio of power. It's quite visually misleading in this image. It doesn't look like it matches up quite that way, but when you integrate under these curves, you do get 50% of the power in the ring. And there's two different geometries, one with a larger spot of 1200 microns versus the smaller 900 microns. The other geometry is a little bit different. This is what we've been terming the tail shaper. This is an asymmetric profile where you still have this high intensity spike that's doing the weld, but you have a tail on that power that's only in one axis, only in one direction along one axis. The idea of this is to reduce the thermal gradients involved in the welding process. So you could use this as a preheating or post-heating. In either direction, the principle is that it should be a slower heating or a slower cooling process, and that should help improve the formation of the grains after the weld. The geometry chosen here is a somewhat educated guess as an initial start point. We'll be looking to improve this in the future. So to start with, I have this high-speed video of welding with the unshaped beam. So this is no beam shaper in place. It's a roughly Gaussian profile that's doing the weld. What I want to highlight here is that the melt pool is quite volatile. There's a lot of motion in there, and you can see every so often there's a bit of material that's being ejected. So what this will mean is the volatility means you increase chances of getting a porous weld. There might be air bubbles getting trapped in there. And the ejected material is going to, it's spatter. It's going to end up where you don't want it. So if we move on to the LTG results, on the left, this is the 900 micron version. First thing to note is that the weld is obviously wider because you've increased the size of the weld pool by distributing more power around it. But it's also a little bit more stable. There's less motion in there. There's less material coming out. And then we have the same again for the 1200 micron case. Again, larger melt pool. And still appears difficult to see when you just quickly flash these up, but it does appear a little bit more stable as you increase the diameter of the ring that you're using for the welding. Onto the tail shaper. Now we've got the two different cases with the same beam shaper. We have tail forward for preheating and tail behind for post-heating. So immediately this is visually much better. There's a lot more stability. There's not so much motion going on behind the weld. There's no material being ejected as far as I can see from the video. It's very smooth looking, and the whole structure that's forming after the weld is quite different. And then the same thing again with the tail behind. Now we're affecting the cooling end of the weld. Again, very smooth. No ejection, and a completely different profile as it's cooling down. So these are just visual images of the resulting welds. We've got the full length of, I can't remember exactly how long, full length of the weld, and then a zoomed in image. The main thing from these is that the volatile nature of the melt pool translates to what you get out as the visual quality of the weld. The unchipped beam is quite messy, quite unstructured. And then as you go to the LTGs, you've got some improvement. There's some more structure in there, and the tail shapers have a much more defined set of features. To make that a bit more quantitative, we have also done electron backscatter diffraction measurements. This is to show the actual grain size in the welds. Immediately, the obvious thing to spot is anything that's black in these images is missing data, which would imply there's a crack. So in the unshaped case, there's a crack all the way down the weld line, which is the exact problem we're trying to solve. The LTG 900 case, there's some small amounts of cracking in there. It's reduced length, but obviously still a problem. Not seen that in the 1200. We're not seeing that in the tail shaper in either orientation. We can also see that the grain size and the morphology here is changing quite a lot as you add beam shaping into the equation. So the LTGs improve this, or make the grain structure finer, and then the tail shapers, it's finer still. In particular, the rear tail shaper, we have a lot of small grains along the center line of the weld, which would imply this should be quite a strong weld as well. The tail shaper forward version still has some of this nice small structure. The LTG is a bit less so. We then run tensile stress measurements, so testing these to their breaking point. The weld with the unshaped single core spot has a tensile stress of about 175 megapascals, whereas for all of our shaped beams, we achieve over 250. So the finer microstructure is actually providing a stronger weld. So in conclusions, we have shown that tailoring the beam shape provides stronger welds, and that this leading, trailing, or an annular intensity profile for pre or post thermal treatment stabilizes the melt pool and improves the weld strength. These significantly affect the weld morphology, grain sizes, shapes, and orientations are changed, and we've achieved approximately 25% increase in the weld strength. This is only a starting point. We've really just shown that the beam shaping gives you an improvement. The next stages will be to find out exactly what beam shape gives you the best. There might be quite some room to optimize this based on how what size of spot you make, how long a tail, what intensity ratios do you use. There's a whole design of experiment to do around this. So to answer the questions, what can we do for you? We provide process enhancement through beam shaping. It's a straightforward modification to existing equipment. There's no need for a full redesign. We can tailor intensity profiles to the process's requirements, and within reason, we can do arbitrary output profile shapes. And what you can do for us, well, we're looking for what challenges are seen in welding where adjusting the thermal profile will help. We can adjust the intensity profile to match that. And we're always looking for partners to work with us to run trials, to find an optimization, to generate the best possible profile and take this to a commercial application. Thank you for your attention.
Thank you very much, Alex. So, any question? I have a question regarding your tail shaper optic. Because the way it works looks like the burst mode in some lasers that they send these small pulses to reheat the material and then send the main pulse to proceed. Did you check or did you compare the results with the optics compared with these burst mode lasers?
No, all of this is in CW. All of this is like high power macro processing. So I guess the difference would be that what we have is a spatial variation rather than a temporal variation. So this is all you have the one input beam, and that's generating both the welding peak and this tail of intensity next to itself. So then as you translate it across, it's doing the heating.
Okay, good. Any final question for Alex? If not, I really thank you for being here today. Thank you very much for your presence. I thank you also to all the speakers that were present today. It was a pleasure. Sorry for the delay in the schedule, but we have some interesting questions that I didn't want to cut. And I hope to see you in the next EPIC meeting. If you find somebody interesting that you want to be connected with, just contact us in the attendees or in the speakers, and we can introduce you by email to discuss any topic that could be make sense for a further discussion. So again, thank you and good afternoon, everybody. Bye, Eugen.
Good afternoon.